If you drag and drop a file into a cloud drive, you are using cloud storage as a simple digital locker. But deploying a functional application in Google Cloud Platform requires an entirely different approach. You have to build an optimized, secure data pipeline. The primary task of a cloud engineer is mapping specific computational workloads to precise storage models based on the required latency, structure, and scale. Once the data has a home, you have to establish a rigid security boundary. Compute resources cannot simply read files. They must be explicitly authorized to access them. Finally, the code that executes the workload must be packaged and sealed, guaranteeing that the deployment process is identical every single time it runs. We are going to construct a containerized extract, transform, and load, or ETL, architecture from first principles. We will start with a completely empty Google Cloud Platform baseline environment and build the infrastructure step by step. Mastering this end-to-end integration, linking storage to security to automated code execution, is the strict threshold you must cross to pass the Google Cloud Associate Engineer certification. Google Cloud offers 3 distinct storage architectures: block, file, and object. Block storage is called persistent disk. It operates like a physical hard drive attached directly to a machine, making it the required option for running operating system boot volumes and relational databases. Databases need persistent disk because they demand intense, low-latency disk input and output, requiring dedicated high-speed storage they can control directly. If you have a fleet of web servers that all need to read the same asset simultaneously, you use Cloud File Store. It provides a shared file system built for high-performance, multi-instance access over a network. Then there is cloud storage. This is object storage, which organizes unstructured data into infinitely scalable buckets, where each individual file is uniquely addressable by a URL. Object storage lacks a true file system structure. Because of this, you cannot run operating systems or databases from a cloud storage bucket. As data ages in these buckets, paying standard rates becomes inefficient. Cloud storage uses object lifecycle management policies to automatically move older files to cheaper, colder storage tiers based on rules you define. This interface shows the Lifecycle Configuration tab in the Google Cloud Console. Here, you apply actions telling the system when to switch objects to different storage classes. If multiple rules conflict, deletion rules always override a change in storage class. If you assign a high-frequency transactional database to object storage instead of block storage, the latency will crash the system. Choosing the wrong storage class causes a pipeline failure before a single line of application code executes. While the Visual Console is useful for learning the architecture, scaling these operations requires the command line interface. Google Cloud relies on a specific CLI utility called GSUtil to execute all operations within cloud storage. To create a new bucket, use the make bucket command, GSUtil MB, followed by the cloud storage path and bucket name. That bucket name must be globally unique, never sharing a name with any existing Google Cloud bucket. To move data into that bucket, you use the GSUtil CP command. This copies files from your local physical machine or a virtual machine directly into the remote storage destination. If you need to transfer an object from one bucket to another, you format the GSUtil MV command with the source bucket path followed by the destination path. Memorizing these specific syntax structures is mandatory. You will use them daily for operational engineering, and they are heavily tested on the certification exam. We now have a secure cloud storage bucket holding raw data and a compute engine virtual machine designed to process it. By default, the VM cannot read the bucket. Google Cloud enforces an implicit deny policy across all resource boundaries. To bridge this gap, you do not use static passwords or hard-coded credentials. Those pose a severe security risk if the execution code is ever exposed. Instead, you use a service account. This is a specific identity ticket created exclusively for a non-human application or virtual machine. Security relies on the principle of least privilege. Assigning broad owner roles to a compute instance is dangerous because it grants sweeping permissions far beyond what the workload requires. You narrow the scope by assigning specific roles, like storage object admin, directly to the service account, granting it only the exact permissions needed to handle the data. The virtual machine absorbs this service account ticket, taking on its identity to gain temporary, scoped authorization to the storage bucket. Once the identity is verified, the pathway opens, allowing the required data to flow securely into the compute engine. Using IAM service accounts is the only architecturally sound method for establishing secure, tightly controlled perimeters between independent cloud components. With the infrastructure communicating securely, we turn to the execution layer, a 56-line Python ETL script designed to transform the incoming data. Deploying raw scripts directly onto a server often leads to dependency conflicts, where the server's pre-installed software versions clash with what the script needs. The industry standard solution is Docker. Docker encapsulates the code and all its dependencies into an isolated, stateless environment that runs identically everywhere. Building this container starts with the core logic file, which we've named etlcloudrun.py. Next, you define a requirements.txt file. This acts as a strict inventory of every external library the Python script needs to function. During the build, the system reads this text file and automatically downloads those dependencies, like the pandas data analysis library, directly into the image layers. The entire assembly process is governed by a blueprint called the Docker file. The Docker file dictates assembly, pulling a Python 3.11 base OS as the foundation block. It sets the working directory, copying requirements.txt file and source code onto that base layer. Finally, it establishes the entry point command to start the application, sealing the environment. This encapsulation process completely eliminates environmental drift. It guarantees that the Python script will execute in the cloud exactly as it did on your local machine. The code is packaged locally. Now it must be pushed into the cloud deployment pipeline. Google Cloud uses Artifact Registry to handle this. It acts as a secure, private organizational repository built specifically to store Docker images. The entire deployment pipeline is triggered by a single command, gcloud build submit. You format this command with a precise deployment string. This specifies the regional destination, your project ID, the exact repository name, and the final tag for the image. Executing this remotely packages the code, executes the Docker file instructions, and stores the final compiled image in the artifact registry. The architecture is now complete. Cloud storage holds the raw data, the Docker container rests in artifact registry ready to execute, and an IAM service account provides the secure bridge between them. A cloud engineer's true value lies here. Success on the certification exam and in the field requires programmatically interlocking storage, security, and automation into a resilient, functioning pipeline.